representing systems of linear equations in matrix form. Hello, everyone. Let's begin our lesson on representing systems of linear equations in matrix form. To start with an introduction, you'll remember from your previous algebra lessons that we often encounter a group of linear equations that all share the same variables, like x, y, or z. When we have a collection of these equations working together, we refer to this as a system of linear equations. Now, you might be thinking, I already know how to solve these using substitution or elimination. And you're absolutely right. Those methods work perfectly for simple problems. However, as we move into more complex mathematics, especially when we start dealing with 3, 4, or even more variables, those traditional methods can become very messy and time-consuming. That is where the matrix method comes in. It provides us with a much more structured, organized, and efficient way to handle these complex systems. Our primary goal for this lesson is to learn a specific skill, how to translate that entire system of linear equations into one single, compact matrix equation. Specifically, we want to learn how to write it in the form a times x equals b. In the next few slides, I will show you exactly how to break down your equations into these three components, a, x, and b. Understanding the components of x, b. Now that we know our goal is to translate a system of equations into the form a times x equals b, let's break down exactly what those three components are. To make this work, we need to organize our information into three distinct matrices: the coefficient matrix, the variable matrix, and the constant matrix. First, let's look at the coefficient matrix, which we denote with the capital letter A. This matrix is made up of the numerical coefficients. That is, the numbers multiplying our variables from our equations. When you are building this, remember that each row in the matrix represents one full equation, while each column represents the coefficients for one specific variable. Now, here is a very important rule. You must ensure that your variables are written in the exact same order in every single equation before you pull them into the matrix. If you switch the order of x and y in one row, the whole system will be incorrect. Next, we have the variable matrix, represented by the capital letter x. This is a column matrix, which means it is a single vertical stack, containing all the unknowns we are trying to solve for, such as x, y, or z. We always write this as a column vector to ensure that the rules of matrix multiplication work correctly when we multiply it by matrix A. Finally, we have the constant matrix, which we call B, just like our variable matrix. This is also a column matrix. It contains all the values found on the right-hand side of the equals sign, the numbers that stand alone without any variables attached to them. Once we understand these three building blocks, we can follow a specific step-by-step process to convert any system into this matrix form, which we will cover in the next slide. Step-by-step process to convert equations to matrix form. Now that we understand what the individual components of our matrices represent, let's look at the actual procedure. How do we take a messy set of equations and transform them into that clean, structured form, a times x equals b, that we discussed in the previous slide? I want you to follow these 5 specific steps. Step 1 is to standardize the equations. Before you even touch a matrix, you must ensure every equation is written in the same standard format, which is a x plus b, y plus c, z equals d. This means you need to move all your variables to the left side of the equals sign and ensure all your constant terms are sitting on the right side. If they are scattered, your matrix will be incorrect. Step 2 is to extract the coefficients. This is where we build our matrix A. You will simply list the numerical coefficients of x, y, and z for each equation into the rows of the matrix. Now, pay close attention here. If you see an equation where a variable is missing, do not just skip it. You must treat that missing variable as having a coefficient of 0. Step 3 is to list the variables. We need to create our variable matrix, which we call x. This will be a column matrix, and you must list your unknowns, like x, y, and z, in the exact same order that you used when you extracted your coefficients in the previous step. Step 4 is to list the constants. Now, we create matrix B. This is also a column matrix, and you will simply take the values from the right-hand side of your standardized equations and list them vertically. Finally, step 5 is to write the final equation. Once you have your three pieces, matrix A, matrix X, and matrix B, you simply combine them into the single matrix equation. A times X equals B. In the next few slides, we are going to walk through some concrete examples to see this exact process in action, so keep these steps in mind as we move forward. Illustrative examples. Now that we understand the theory behind the components of our matrices, let's put it into practice with our first concrete example. Take a look at this system of two variables. We have two linear equations here, 2x plus 3y equals 8, and the second equation is x minus 2y equals negative 3. Let's break this down step by step, just like we discussed in the previous slide. First, we need to identify our coefficients to build matrix A. Looking at the first equation, our coefficients are 2 and 3. Moving to the second equation, remember to be eye on that negative sign. The coefficients are 1 and negative 2. When we place these into our coefficient matrix, we get a 2 by 2 matrix with 2 and 3 in the first row and 1 and negative 2 in the second row. Next, we identify our variables for matrix X in this system. We are solving for X and Y. As we learned earlier, this must be written as a column matrix, so we have X over Y. Third, we look for our constants to create matrix B. These are the values on the right-hand side of the equals sign. For our first equation, it is 8, and for the second, it is negative 3. Again, we write this as a column matrix, with 8 over negative 3. Finally, we bring it all together into the final matrix equation. We represent the system as our coefficient matrix, multiplied by our variable matrix, equals our constant matrix. Specifically, the matrix with 2, 3, 1, and negative 2, multiplied by the column matrix of X and Y, equals the column matrix of 8 and negative 3. This structure is exactly what we will use when we tackle more complex, three-variable problems, like the fruit vendor scenario coming up in the next slide. Real-world application, 3 variables. Imagine a fruit vendor who sells 3 different types of gift baskets. The first basket contains 1 kilogram of apples, 2 kilograms of bananas, and 1 kilogram of cherries, for a total cost of $15. The second basket contains 2 kilograms of apples, 1 kilogram of bananas, and 3 kilograms of cherries, costing $25. The third basket consists of 3 kilograms of apples, 3 kilograms of bananas, and 2 kilograms of cherries, with a total price of $30. To find the individual prices, we first need to define our unknowns. Let X represent the price per kilogram of apples, Y represent the price per kilogram of bananas, and Z represent the price per kilogram of cherries. Now, let's follow the step-by-step breakdown we learned in the previous slide to convert this information into matrix form. Step 1. We formulate our linear equations. Based on the basket contents, our equations are 1x plus 2y plus 1z equals 15, 2x plus 1y plus 3z equals 25, and 3x plus 3y plus 2z equals 30. Step 2. We construct the coefficient matrix, which we call A. We extract the numbers multiplying our variables to create a 3 by 3 matrix. The first row is 1, 2, 1, the second row is 2, 1, 3, and the third row is 3, 3, 2. Step 3. We create the variable matrix, X. As we discussed earlier, this must be a column matrix containing our unknowns, X, Y, and Z. Step 4. We construct the constant matrix, B. This is a column matrix containing the values from the right-hand side of our equations, 15, 25, and 30. Step 5. Finally, we write the complete matrix equation in the form A times X equals B. This is represented as the matrix with rows 1, 2, 1, 2, 1, 3, and 3, 3, 2, multiplied by the column matrix of X, Y, and Z, equals the column matrix of 15, 25, and 30. Now that we have mastered the two-variable approach, let's apply these steps to a more complex, real-world scenario involving 3 variables. As we move to the next slide, I want you to pay close attention to how we extracted these numbers, because there are some very common mistakes students make when organizing these values. Common mistakes to avoid. First, be very careful not to ignore the signs. A common error is forgetting the negative sign attached to a coefficient. For instance, if you are looking at the equation x minus 5y equals 10, the coefficient for y in your matrix must be negative 5, not just 5. Always check if a term is being subtracted. Second, keep an eye out for missing variables. Sometimes an equation might skip a letter, like in the case of 2x plus 3z equals 5. In this scenario, students often forget that y is still part of the system. You must remember that y is present, but its coefficient is 0. Therefore, your row in matrix should be written as a 2, 0, and 3. Third, pay close attention to your matrix dimensions. Remember from our earlier discussion on the components of x equals b that the variable matrix x and the constant matrix b must always be column matrices. If you accidentally write them as row matrices, the matrix multiplication of a times x becomes mathematically impossible. The structure must be vertical to work. Finally, ensure your variables are ordered correctly. If your first equation is x plus y equals 2, but your second equation is written as y plus x equals 3, you cannot simply extract the numbers as they appear. You must rearrange the second equation to x plus y equals 3 before you start. This ensures that every column in matrix corresponds correctly to the same variable in matrix x. Now that we have seen how to successfully convert equations into matrix form using our fruit vendor example, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make small clerical errors that will lead to the wrong answer. Let's look at 4 specific mistakes to avoid. If you can avoid these 4 mistakes, you will be well on your way to mastering this topic. Let's move on to our final summary of the key takeaways. Key takeaways. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. First and foremost, remember that the main goal of what we've learned is that any system of linear equations, no matter how many variables it has, can be compactly and elegantly represented by the single matrix equation. A times x equals b. To make sure you can build this equation correctly, let's quickly recap the 3 components we discussed earlier. First, there is matrix A, which we call the coefficient matrix. This matrix is simply the collection of all the numbers multiplying your variables. Next, we have matrix X, the variable matrix. As we emphasized during our step-by-step breakdown, this must always be a column matrix containing your unknowns like x, y, or z. Then, we have matrix B, the constant matrix. This is also a column matrix, and it consists of the values found on the right-hand side of your equal signs. Finally, and perhaps most importantly, always ensure that the order of your variables is consistent across every single equation. If your first column represents x, then every row in your coefficient matrix must follow that same pattern. Maintaining this order is essential to keep the integrity of your matrix representation and to avoid the common mistakes we looked at in the previous slide. If you keep these points in mind, you'll be well prepared to handle much more complex systems in our next lesson. Great job today!